Let's finish up our trig review. Hopefully we can finish it up. So we just did the unit circle. So hopefully you just did the unit circle test. So hopefully some of this is fresh on your mind. But let's do a quick recap. Make sure you're not regressing. First off, definition. What is pi?
What?
The amount of radians.
They can fit it in the circumference of the circle.
Circumference of half a circle.
Half into the diameter.
What?
Circumference over diameter.
Circumference over diameter. It's the circumference over the diameter. We typically write the diameter as 2 radiuses. Circumference over diameter. If I have a circle and it has some diameter, how many of these diameters would it take for me if I had that as a string to wrap all the way around the circle? And it would take me roughly 3.14. If I did a perfect circle with a perfect diameter, it would take me exactly pi. That's what pi is by definition. The ratio of circumference to diameter. Okay, what is 1 radian?
It is the angle of radius.
The radius in the circumference.
It is. So now, rather than wrapping around a diameter, which would, if I wrapped around a diameter, that would take me like to here. We're just going to wrap around a radius, which would take me like to there. So take that length, wrap it around. The angle that this makes is 1 radian. The radian is the angle associated with an arc length of 1 radius. This is 1 radius, then this angle is 1 radian. Make sense? All right, definition of sine. What is sine?
Sine is the x coordinate.
The y coordinate.
The y coordinate.
So if I give you now, this isn't necessarily 1 radian. I give you some random angle theta. And we're on the unit circle, which means the radius of our circle is what?
1.
1. The unit circle is a circle with the radius 1. So our radius here is 1. And I give you some angle. 60 degrees, whatever. Then the x-coordinate here is, by definition, cosine of theta. And the y-coordinate is sine of theta. You with me? By definition.
Yeah.
So looking at this picture, looks like cosine of theta in this case is about, I don't know, 0.7. And it looks like sine of theta is about, I don't know, 0.8. Just looking at the picture. Looks like there'd be numbers close to those. What exactly they are, well, we only figure that out for very specific values of theta, which you did on your unit circle. You found the x and y coordinates at very specific angles, which gives you the sine and cosine at those very specific angles. You have your unit circle in front of you, right? So if I were to ask you, what is the cosine of 3 pi fourths? What is it?
Root 2 over 2 negative sine 1.
You look at your unit circle. You see where's 3 pi fourths on your unit circle.
Yeah.
You see it?
Yeah.
What's the x coordinate?
Negative.
2 square root 2 over 2.
You're wondering if you got it right? Waiting for him to say it.
No, I did get it right, but I didn't know how to say it.
Negative root 2 over 2.
Root 2.
Yeah. So there it is. And you could give me any other one. I could ask you for what's the sine of 3 pi halves?
Negative 1.
Negative 1. 3 pi halves is at the bottom. Negative 1. Oh yeah. Look at the y, not the x. And so now you can figure out the sine and cosine for all the angles you have on your unit circle. Which is the same as what most trig students can do.
Sweet.
So there's a sine and cosine of those. Now if I ask you for something like the tangent of, what should we do? Let's just do pi fourths. What's the tangent of pi fourths?
Here's 1.
All right, now we're in trouble. So let's remind ourselves of these other definitions. So you remember what sine is. This always gives us the y coordinate on the unit circle. You remember what cosine is. That always gives us the x coordinate of that angle on the unit circle. By definition, tangent of theta is sine of theta over cosine of theta. That's its definition. So what is tangent of pi fourths?
Root 3 over 2 or 1/2.
Pi fourths.
Oh.
You're looking at pi thirds. We'll do pi thirds.
No, let's do.
So looking at pi thirds.
So
You're
it's
root 3 over 2.
3 over 2 over 1/2.
All over 1/2.
Root 3.
Now you're not dividing one fraction by another fraction. It is the same thing as you take the numerator and you multiply it by the reciprocal of the denominator, right?
That's how they do
Right?
it. Right.
Or you can just see the 2's go out and cancel them out, whatever works for you. But now the 2 and the 2 cancel, and you're left with square root of 3 over 1, or just square root of 3. And then roughly speaking, what is the square root of 3?
Like 1.7.
That's going to be higher than that, but not quite 2.
1.8.
What's 18 times 18?
36.
It's 1.73205.
Whoops.
The square root of 3 is? Oh! Thank you. Yeah, 17. Good. You're right. I was thinking that for square root of 2 for some reason. And so I think it's got to be above it. But square root of 2 is 1.41. All right, good. So yeah, this is roughly 1.7.
Right.
And if you look on the unit circle at that angle, 60 degrees, I was pretty close to it. Tangent, remember, so we're looking at this one. We're pretending that this angle here is pi thirds. You with me?
Okay. Why not 60 degrees?
This is 1, 60 degrees, pi thirds, same thing. Now this comes down. What is the distance from here to here?
0.7. I mean, it looks like a half.
Yeah.
7. Oh, it's a half.
It's exactly half. What is this? It's the x-coordinate of this point.
Oh.
What's the x-coordinate at pi thirds?
1/2.
1/2. How tall is it?
3 root 3 over 2.
Root 3 over 2.
I'm looking at your other 0.7.8 numbers.
Yeah.
Root 3 over 2. Oh yeah, forget those. Sorry. Root 3 over 2.
It's pi thirds.
So, notice that what tangent just did. It did the y over the x. We did the y over the x. That's rise over run. What's rise over run?
Slope.
Slope. It gives you the slope. So notice that the slope here, it's not quite a slope of 2. That would be like that. It's not a slope of 1. That would be like that. Somewhere in the middle. Kind of makes sense. Right?
Yeah.
So tangent gives you slope. Let's try another one. Let's do tangent pi fourths now.
Gives you.
Actually, let's do 3 pi fourths. Tangent at 3 pi fourths.
So negative root.
So that's this
oh.
point over here.
So that's 2 over
What's
2.
the height?
2 over 2.
Root 2 over 2. And what's the x?
Negative root 2 over 2.
Negative root 2 over 2. Now, in general, if you see x divided by negative x, what does that equal to?
Why? Negative 1.
Negative 1. We can pull the negative out. What's x divided by x? What's any number divided by itself?
1.
1, unless it's 0, but obviously we're not 0 here. So what's root 2 over 2 divided by root 2 over 2? 1. Add the negative. So this is negative 1. It has a slope of negative 1. And what does a line with a slope of negative 1 look like? That looks like a line like this. Sorry, missed my origin. So it has a slope of negative 1. And we could have guessed that just by looking at the slope.
Yeah.
Because it goes over this way. Well, going from here to here, we think about it, it goes down square root 2 over 2 and over square root 2 over 2. Slope of negative 1. It's going down. Right? Slope of positive 1 would be this one going up, which goes through pi fourths. So the tangent of pi fourths is 1. And the tangent of 3 pi fourths is negative 1. Question. What would be the tangent over here at 5 pi fourths?
1.7.
It'd still just be 1. That's the same slope as this line. Or you can plug it in and you get negative root 2 over 2 over negative root 2 over 2.
Yeah.
And you get 1. Okay, so that's what tangent gives us. Thought tangent by definition is just sine over cosine. Tangent is sine over cosine. So if you know how to do sine and cosine, you're fine with tangent. More insight to tangent, it's the slope. If you can't remember that, just remember sine over cosine. That's its definition. And now we have the other 3 weird trig functions that we use far less. Cosecant is just defined to be 1 over sine. secant is just defined to be 1 over cosine, and cotangent is just defined to be 1 over tangent of theta. So they're just the reciprocals. You with me?
Yeah.
Now let's throw our unit circle up here one more time. Has a radius 1, some angle theta we don't know. And let's look at this right triangle. What is the base of this right triangle?
We don't know.
X.
What is it in terms of theta?
Oh.
What is the x coordinate at this point?
Cosine.
If this angle's theta, what's the x coordinate at this point?
Cosine theta.
Oh.
We don't know what the angle is. Don't read too much into my picture. Maybe that's pi 6, maybe that's pi thirds, maybe it's pi fourths. We don't know what it is.
What's X?
But for some angle, theta, what is the x coordinate at this point? You do. What gives us the x coordinate? If I know the angle theta, what gives me the x coordinate at this point?
Are you specifically asking me?
Yeah.
Well, I don't know.
Chandler, go ahead.
Let's go back to these. By definition, what is sine of theta?
Why?
It's the y coordinate at angle theta on the unit circle.
So cosine.
So cosine.
Oh.
What's the x coordinate here? Cosine of theta.
Oh.
So what is this distance right here?
Theta.
Cosine of theta. All right, this is cosine of theta. And what's the height of this triangle?
Sine.
Sine of theta. Now, does it matter that we drew this triangle inside of a circle?
No.
If I pull out this eraser and I get rid of this, did that change anything about the triangle?
Whoa.
No. So it's still the case for any triangle. If the hypotenuse is 1, then the bottom is cosine of theta. So if you knew the hypotenuse and you knew the angle, you can figure out the x and you can figure out the y, right?
This is true.
Now let's get crazy with it. What happens to this length if I double this length? Let's say I take that triangle now and I stretch it. So now, rather than the hypotenuse being 1, the hypotenuse is now 2.
Whoa.
What happened to the length down here?
It doubled.
It doubled. So now this is 2 cosine of theta. And what happened to the height?
Doubled.
It doubled. So now this is 2 sine of theta. Right? What if I would have gone the other way? What if I would have shrink down the triangle? So its hypotenuse was 1/2.
Then that's a true.
Then these would be 1/2. And 1/2. Right?
Yep.
So for any r, let's just say now this has a distance r. What's this going to be?
R.
R cosine of theta. And what's this going to be? R times sine of theta. So now if I gave you some random triangle, notice that you can now figure this out. I tell you this is an angle of 60 degrees. I'm saying that we're looking at someone's roof. Its pitch is 60 degrees, and I measure from the bottom of the roof to the top of the roof, and I measure that that happens to be 10 feet, or 20 feet, or something like that. We'll say it's 20 feet. Question: how far over did we walk while walking up the roof? How far this way did we go? We need to find this. This is going to be 20 times cosine of theta, in this case 60 degrees, feet.
Okay.
And what is cosine of 60?
Whatever.
1/2. So it's going to be 1/2 times 20, which is 10 feet. You have walked over exactly 10 feet in walking up the roof.
Okay, that's
How high up the roof did you go? Maybe you want to know how high up you are.
27.
You're climbing up on the peak of this roof. You're thinking, can I survive this jump off without breaking my leg? You know that the building's, whatever, 10 feet tall. And you know from practice that you can get away with 17 feet. Anything higher than that, you're in trouble. So we're going to try this out. Can you jump off this roof and not hurt yourself?
Yeah.
You know your limit's 17 feet. Very practical scenario that you come across all the time in day-to-day life, right?
Yeah.
All right. So this is 10 feet up, plus we have this. So now we need to figure out how high this is. How high is this?
20 cosine of theta.
20 sine of theta.
Or
20 times sine of what?
Theta.
60 degrees. Not this angle, this angle. This angle up here would be 30 degrees. Okay, what is sine of 60 degrees?
3.
Root 3 over 2. Root 3 over 2 times 20 gives us 10 squared to 3. So this is going to be 10 squared to 3 feet. Which is going to be just over 17. Oh, this is a tall roof. I didn't think about this enough. So this right here is going to be roughly 17 feet.
So can you do it?
Yeah, we'll say, you know, you can survive 20 feet, all right, with being okay. So this is 17 feet, and you're 10 feet in the air. So if you get to the very top of that roof, you're 27 feet in the air.
Okay.
Okay. No, you couldn't.
No chance, right? So if we have some general triangle here, and we call this side y, and this side x, in general, x is always equal to r times cosine theta, right?
Right.
That's how we get the x.
Okay.
That's what we just did. And in general, y is equal to what? R times sine of theta. Now, solve this for cosine of theta real quick. Solve this equation for cosine of theta. What does that tell us? Cosine of theta is equal to what?
In x.
In terms of x and r. What does cosine of theta equal? If x equals r cosine of theta, solve this equation now for cosine. Look, if 20 is equal to 10x, what does x equal? 2. How did you do that? You divided both sides by 10, right? What do I need to divide both sides by to get cosine by itself? R. So cosine is equal to x over r.
I knew that.
Of course you knew that. Everyone knows that. All right, and what does sine of theta equal?
Y over r.
Y over r. And we've already talked about this one. What does tangent of theta equal?
That's what you get.
X over r.
So yeah, let's do some scratch work over here and I'll write it over there. Tangent of theta is equal to sine of theta over cosine of theta, right? What was sine of theta?
Y over r.
Y over r. What's cosine of theta? X over r. What does that equal?
Y over x.
Y over x. R's go out. And you already knew that. Tangent gives you the slope. The rise over the run. Rise over run. Tangent of theta is y over x. Right?
So ways to simply explain that. I just memorized over A and A over A.
Yeah, you might memorize SOHCAHTOA.
Sohcahtoa.
So sometimes you're told SOHCAHTOA. So remember this. What do you do when you stub your toe? You SOHCAHTOA. Here's the way other people explain it. I'll give it to you in case it's useful. So means sine is opposite over hypotenuse. The sine of this angle is the opposite side, y, over the hypotenuse, r. Sine is y over r. So, cosine is adjacent over hypotenuse. Here's your angle, here's the side, here's the leg adjacent to the angle. So cosine is adjacent over hypotenuse. Or in other words, it's x over r. TOA, tangent, is opposite over adjacent. Here's our angle. What's the opposite of our angle? That's the y. Which one's adjacent? The x. It's y over x. So sometimes you're told SOHCAHTOA to memorize these things. I don't like tricks like that. I like just knowing what sine and cosine are and then thinking about this triangle. But whatever helps. Now we have these other trig functions. Cosecant, secant, and cotangent. Oh goodness, this is turning into a pain. You just need to remember what each of them are associated with. Cosecant is just the inverse of sine. So if sine of theta is y over r, what is cosecant of theta?
R over y.
It's just r over y. And what is secant of theta?
R over X.
R over x. And what is cotangent of theta?
Y over R.
Y over r.
No, it's X.
X over y.
Actually,
And so each of the 6 trig functions just correspond to each of the 6 possible ratios you could take of this triangle. Right? We have an x, a y, and an r. What are all the possible ratios you can make with those? All the possible fractions. Well, I could do the x over the y or the x over the r. If we do the x over the y, that's cotangent. You do the x over the r, that's cosine. So for each of the 6 possible ratios, you understand how there's 6 possible ratios I can make with x, y, and r?
Yeah.
Back to a simple counting problem. A ratio means between 2 numbers. I need to pick a number to go into the top and pick a number to go into the bottom. How many options do I have for what number goes at the top out of x, y, and r? 3. So there's 3 ways I can choose that. Times, now I need to pick something different to go in the denominator. Because if I pick the same thing, I just get 1. 2. So 3 times 2 is 6. There's 6 possible ratios that we can make with this triangle. For each of the 6 possible ratios, we made up some function that corresponds to it. Sine, cosine, tangent, blah, 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 blah. They're just the 6 possible ratios. That's all they are. So if you know your triangle, you can now figure out sine, cosine, tangent, any of it real easily. Right? So let's write out a typical triangle as a concrete example. We'll say that's 60 degrees. We'll say down here is 10. We'll say over here is 20. And we'll say over here is 10 squared to 3. Where have I seen that triangle before? Oh, it's the one we just did there. Okay. So we're looking at this triangle. Now I'm going to ask you, okay, so now what is tangent of 60 degrees equal to?
Oh, wait.
We already figured it out using the unit circle, but we didn't have to use the unit circle. We could use this triangle. It's y over x. What's 10 squared to 3 over 10? It's just square root of 3, which is what we already found for tangent of 60 degrees, just using a unit circle. Because it's the exact same triangle, just scaled up. The ratio stays the same. Right? We can do this again to figure out what would be cosine of 60 degrees. You already know from your unit circle that cosine of 60 degrees is 1/2. Right? That's on your unit circle. But you could also look at this. Cosine is equal to x over r. X is 10, r is 20. 10 over 20 is... Holy cow, it worked. So that's all these trig functions are. They're all the possible ratios for right triangles at some angle theta. Make sense? Okay, so now we're just going to prove a bunch of identities. Unfortunately, I didn't really get these identities from a book. I just looked up a page of trig identities online. And I'm just going to prove them all. Or as much as we can get through. Now, before I do that, I found out that you guys don't know one of the 2 things you used to be able to count on all students to know. 2 theorems that students knew coming out of high school. One, the Pythagorean theorem. The second one is the quadratic equation.
Oh, I know that one.
You know it?
I hate it. Right there on top of my head.
What is it?
I can't tell you it now because I forgot it.
That's not good.
I have to. I used to.
This is something that you should have memorized. I'm not a huge fan of memorizing things, but there's a few things that you should just memorize. Here's one of them, the quadratic equation. So let me derive this for you really quick. So I give you some quadratic, ax squared plus bx plus c, and it's equal to 0. I want to know the x's that make this true. For any numbers you choose a, b, and c, I want to find the x's that make this true.
2.
So that 0 won't work because c could be a number.
That's not. For any A, B, C, there's one X and
I want to come up with some formula, some way that you could always figure this out. For any a, b, and c I give you. So that if I give you 2, 10, and 3, you can give me the x's associated with that. I want you to give me the x's such that 2x squared plus 10x plus 3 equals to 0. Now you learned how to factor these things, and you can sit there and think about it and factor it maybe. You'll come up with the numbers. Or you can come up with a general way to do it for any three numbers, A, B, and C. And that's what I'm going to do. I'm going to show you the general way to do this no matter what. And that's what the quadratic equation is. It's how you find the x's that always work, no matter what A, B, and C are. Assuming that there are x's that can make it work. If there are x's that can make it work, this will give them to you. You with me? You understand what it does? Alright, so let's do it. So I know ax squared plus bx plus c equals to 0. First thing I do, move the c to the other side. And I'm going to divide everything. Well, let's not do too many steps in one go. Don't want to lose it.
Donnie, can I use your restroom?
Sure.
I'm also excused
At
at 10:15.
10:15.
Looks like we just lost two of them.
I forgot.
Oh, you really weaseled out of that. Well, we better hurry because Debbie needs to know this.
Okay, go.
Alright, next thing I'm going to do, divide everything by a. So x squared plus b over ax is equal to negative c over a. Right? Just divide everything by a.
Okay.
Okay, now I'm going to add a fancy number to both sides of the equation. But since I add it to both sides, it's not going to change the equation. So I'm going to say x squared plus b over a plus plus b squared over 4a squared is equal to negative c over a plus b squared over 4a squared. So I add the same funny expression to both sides.
Now you can minus them.
Well, now I can factor this side.
Oh yeah.
So now this side I can rewrite as x plus b over 2a squared is equal to negative c. Let's get a common denominator here between this and this. What do I need to multiply this term by to get the same denominator as this? I need to multiply top and bottom by 4a. All right, so we get negative 4ac plus b squared all over 4a squared. Right? Okay, now notice that this is the same thing as this. What's x times x?
X squared.
X squared. What's x times b over 2a? That's x times b over 2a.
Whoa.
But then we have b over 2a times x gives me another one of those. So I'm going to have 2. When I multiply this out, I'm going to have 2 times x over ba, which is the same thing as the 2's go out, and it's going to be b over a x, which is exactly this term.
Yes.
And finally, what's this term times this term?
That term squared.
That term squared. The numerator times the numerator gives me b squared. 2a squared, 2 squared is 4, a squared is a squared. So this is the same thing as that. And what we did there is called completing the square. You can search a little video on how to complete the square if you're curious about that. Okay, now what do? Take the square root of both sides.
Okay.
You with me?
Yeah.
So x plus b over 2a is equal to plus or minus the square root of this whole thing. Now I'm going to write the b squared first, minus 4ac. Change the order there. B squared minus 4ac. All over, I'm going to rewrite that 4 as 2 squared, just so you can see it. 2 squared times a squared. With me?
Yeah.
Okay. Now this is equal to, x is equal to, move this to the other side. So it's equal to negative b over 2a. So I subtracted b minus 2a from both sides.
Yeah.
Plus or minus. The square root of a term is the square root of the numerator over the square root of the denominator. So square root of b squared minus 4ac all over the square root of the denominator. What's the square root of 2?
2.
Or sorry, what's the square root of 2 squared?
2.
2.
What's the square root of a squared?
2.
A. So the square root of 2 squared times a squared is just 2a. Oh, they have the same denominator. So now I can rewrite with that denominator. And so it's equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's your quadratic equation. That's what x would be equal to. And this works for any a, b, and c you give me. So now if a is 1, b is 10, and c is 3, plug in 1 for a, 10 for b, 3 for c, and this will give you your x's.
1 for a.
Oh, sorry, that's what I thought I said.
Oh.
Plug in 2 for A, 10 for B, 3 for C. Plug into there, and it will spit out the x's that make this true, that make it equal to 0. Or that make it equal to 0. So there's a quadratic equation. And it's one of those things that you just need to memorize. But there's a derivation of it for you.
It's so much fun.
Good? Now let's jump into trig identities. And I'm just going to take them as I roll them down. I'm not sure if this is a good order. Just what I saw online. So the first trig identity is to prove that sine squared of theta plus cosine squared of theta is equal to 1. You can go. So that's the first thing we're going to do. Let's look at our unit circle. Unit circle, draw some triangle on it. Since it's a unit circle, at some angle theta. Since it's a unit circle, what is the hypotenuse on the unit circle?
1.
1. It's a unit circle. The hypotenuse is just 1.
Right.
What's this side's length? Now, you guys already got stuck on this like twice today. On the unit circle, what is the x length?
1/2.
It's the same as the x coordinate here. We don't know what it is because that's a random theta.
Oh. Okay.
So how do I figure out what the x length is?
Go backwards from
You.
What? How'd you get one?
It's just cosine of theta.
60.
Oh, right.
Goodness, you guys.
Sorry, this takes a minute for cosine and
This length is cosine of theta. What's the height?
sine. of theta.
Sine of theta. And what does the Pythagorean theorem tell me for any right triangle? This side squared plus this side squared equals this side squared. So the Pythagorean theorem tells me that cosine squared of theta, that's how you say cos. You probably want me to write cosine of theta squared. Cosine of theta times cosine of theta. This is how we write it when it's a function like that.
Okay.
So cosine squared of theta plus sine squared of theta is equal to 1 squared. What's 1 squared?
4.
1 times 1 is
1.
1! Okay, there's the first trig identity. Sine squared plus cosine squared equals 1. Right?
Yeah.
Alright, let's move on to the next one. The next one says tangent squared plus 1 is equal to secant squared. Now I'm going to pick up from here, and I'm just going to try and make tangent squared show up, since that's the first thing I see. I see it's tangent squared. I'm going to make tangent squared show up. What is tangent?
It's the.
Sine over cosine.
Sine over cosine. I got a sine there. Let's just divide it by cosines.
That's not
You with me?
cosine squared.
So I'm going to start with this equation, and I'm just going to divide everything by cosine squared. So this right here is going to turn into cosine squared of theta over cosine squared of theta. This right here, oh, sorry, that's plus. Plus this is going to be sine squared of theta
Cosine squared.
over cosine squared of theta is equal to 1 over cosine squared of theta.
Or in
Right?
other words.
What's cosine over cosine?
1.
Squared,
1.
still 1. 1 plus sine over cosine is Tangent. Squared is tangent squared. And now 1 over cosine is, which one's 1 over cosine? These ones are kind of weird, you just have to memorize it.
Secant.
Secant. So this is equal to secant squared, perfect. And that's probably what we were looking for.
Yeah.
Oh, there it is.
Lo and behold.
Crazy.
Wow.
Now let's prove the next identity. Yeah, told you, tric's easy. You just gotta memorize a few things and then you just play with it.
Yeah.
And it just falls out.
Until you get those last ones.
It does seem
Ah, we'll see.
Well, until you get to.
We'll see where we get
one
stuck.
of the cosines.
Let's do this one now.
Guys,
So this one, I'm going to start at the same spot. So I'm going to go back and reset to here. And now we're going to prove this one. So now I need a cotangent to show up. What's cotangent?
The opposite
cotangent
of tangent.
is
Inverse.
1 over 10.
It's 1 over tangent, or tangent sine over
Or
cosine.
the inverse.
So it's the same thing as cosine over sine.
Well, they definitely.
It's just a reciprocal of tangent.
Got it.
Mm-hmm.
Okay. So I need to come up with cosine over sine. So starting with this one, I have a cosine there. Let's divide everything by sine.
Genius.
So cosine squared divided by sine squared is going to give me cotangent squared. Sine squared divided by sine squared is going to give me,
1.
You know.
and 1 divided by sine squared is going to give me, what's 1 over sine? Cosecant. So it's going to give me cosecant squared. I finally realized what you were doing. It's like when you hear a kid trying to read it and they say, eh. The. All right. There, we proved that one. Okay, on to the next one. For the next one, this says sine of negative theta is equal to negative sine of theta. Let's show that. So here's our unit circle. Pick some random angle theta. Here's theta. What does negative theta look like? Just going down theta, right?
Yeah.
Negative theta gets us right here. Now, if this point right here, what is the y-coordinate here? This is a unit circle.
Sine of.
Sine of theta.
Yeah.
Sine of theta. What is the y-coordinate here?
Negatives or.
It's just a negative of whatever it is up here. It's this point flipped over.
Right.
So it's negative sine of theta. But that's also just the sine at the point negative theta.
Right.
It's the y-coordinate at negative theta. It's the same thing as the y-coordinate here, but negative. Flip down.
Square box.
So negative sine of theta is the same thing as sine of negative theta.
Oh, that's what. Why did
Now
I-
let's do cosine.
It's so simple. Yeah.
Let's see. Cosine of negative theta is just the same thing as cosine of theta. Let's look at that one. Shouldn't have erased my picture.
Oh, this might be a little bit harder.
No, it's identical.
Easier.
Here's negative theta. Here's theta. The x-coordinate at this point is
Cosine of theta.
cosine of theta. The x-coordinate here, this goes over cosine of theta.
That's right.
So how far over does this point go?
Negative cosine of theta.
No, it goes over the exact same far.
Oh yeah, that's what.
So let's go cosine of theta. So how far over are we at negative theta? We're at the same place we were at just theta. So cosine of negative theta is the same thing as cosine of theta. They have the exact same x-coordinate.
Okay.
Straight facts.
Or the way you were probably told it is cosine is an even function. That helps when you graph out the functions, but we're not going to graph these out. That takes too much time. All right, I lost where. Oh, we did that one.
Tangents.
All right, let's do tangent. What's tangent at negative theta?
A negative.
Well, that's sine at negative theta
Over cosine.
over cosine at negative theta. But look at what we just proved. What is sine at negative theta?
Negatory.
Sine of negative theta is negative sine of theta.
It's true.
What is cosine of negative theta?
Cosine.
Just cosine of theta. So we get negative sine of theta over cosine of theta. Or in other words, we get negative sine over cosine or negative tangent of theta. So tangent of negative theta is just negative tangent of theta.
Beautiful.
And we can do similar things for secant. Secant's just going to do the exact same thing that cosine does. Cosecant's just going to do the same thing that sine does. And cotangent's just going to do the same thing that tangent does.
Yeah.
So those three we get for free. All right, let's move on. Next identity. Sine of pi halves minus theta is equal to cosine of theta.
Ooh, that's cool.
Yeah. Let's draw a triangle here. We're going to call this our theta. This is a right triangle. Now, question. If you know theta and you know this is a right angle, what's this side up here? Let me draw a second triangle for a second to specify my point with some variables. If I know this is a right angle, and this is alpha, and this is beta, what do alpha plus beta have to equal?
90 degrees.
90 degrees. Or pi halves, same thing, right? In radians. Pi halves are 90 degrees.
So that angle equals
So-
90 degrees, subtract theta.
So if we call this other angle up here x, what does x equal?
90 degrees, subtract theta.
We know that theta plus x has to equal 90 degrees, or pi halves, right?
Right.
So x is just equal to pi halves minus theta. You with me? So this angle up here is pi halves minus theta. Good?
This is true.
Alright. Now let's see our connection. And this is some distance r we all know. R. What is this distance right here?
That would be the
Cosine of, or sine of.
Cosine, because it's
cosine of
x.
theta.
cosine of theta times r, because we're no longer just 1.
Oh, okay.
So this is r cosine of theta, right?
Yeah.
Yes.
And this right here is r sine of theta. Let's erase those now. And the height here is r times sine of theta. That's if you're looking at the triangle like this, right? Now, let me draw that exact same triangle again. A little bit different. Still a right angle. Now our theta's up here. This is still r. And our pi halves minus theta is down here. So I'm just taking this triangle and I'm tipping it up. You with me?
Mm-hmm.
Yeah.
What's our x here?
R times sine of theta.
R cosine of this angle.
Oh.
So this is r times cosine of this angle, which is pi halves minus theta. Right?
Yeah.
And what is our height here?
What is sine?
We do sine. Sine of the angle. This is r times sine of this angle, which is pi halves minus theta. So notice that this side is the exact same as this side. We just flipped the triangle. So r sine of pi halves minus theta is equal to r cosine of theta. Cancel out the r's, and what are we left with? We're left with sine times pi halves minus theta is equal to cosine of theta, which is this.
That's so
Similarly, look at this. This side is the same as this side. So cosine of pi halves minus theta is the same thing as sine of theta.
Which is that?
Which is that? So we proved those two. Tangent. Tangent, now you just plug in what we know about sine and cosine. So tangent of pi halves minus theta is equal to sine of pi halves minus theta over cosine of pi halves minus theta, which is equal to sine of pi halves minus theta is the same thing as what?
Tangent. Oh.
That's what we just proved.
Oh, it's cosine over theta.
The cosine of theta.
Over theta? Over.
Sine of pi halves minus theta is cosine of theta. Similarly, what's cosine of pi halves minus theta? That's what we just proved in the previous problem. Sine of theta.
That looks
So you get cosine over sine, which is
Tangent.
cotangent.
Oh, yes.
Tangent is sine over cosine, cotangent. We don't need the parentheses when we do the theta. I got that. Cotangent of theta. All right, so we just proved this one.
Yes.
These next ones, I don't think we really need to prove. I think you kind of get it, but we'll just make sure. So if I've got some angle here, theta, and I tell you that the y-coordinate here is exactly 0.79. That's how high it is.
Okay.
How far up would I be now if I went all the way around the circle back to that point?
Probably about the same.
I'd be at the exact same point. I went all the way around the circle. So that's what this is saying. However high you are at theta is how high you are if you add 2 pi to theta. If you go around the whole circle, you're back where you started. Same thing with cosine. And then tangent is just a ratio of, tangent is with when you add a pi. Maybe we can see that one with the circle really quick. Remember, tangent gives us a slope, right?
Yep.
So, let's pick some angle, theta. Notice that the slope of this line is identical as the slope at the point on the opposite end of the circle. Here's the slope at theta. If we go to the opposite end of the circle, that lands on the same line. Both these points have the exact same slope.
Yeah.
So the point at theta and the point at, what's this angle? What's our angle all the way to here?
Theta plus 180.
We added 180 degrees. Or we added pi. So this is theta plus pi. So if you go to the other side of the circle, you have the exact same slope of the line. So that's what this says. Tangent at theta plus pi is still just tangent at theta. Same slope. All right, next one. Okay,
Now it gets
probably our hardest one.
Weird.
Oh joy.
Okay. This picture could get a little bit messy with triangles, so let's make it nice and big. Just draw a quarter of the circle. That was meant to be a circle.
It's a door.
Okay, now I'm trying to find the sine at an angle. We'll do alpha, we'll do the plus case first. So first I'm going to try and figure out what the sine of alpha plus beta is when we add two angles together. So let's do some dotted line to help us keep these straight. That's going to be to alpha. This is going to be to beta. Oh, that black marker is good. Maybe we need to separate these more. Let's make our beta bigger. Beta is going to be to here. Alright, so this angle right here is beta. And the red here is going to be alpha. And so we are trying to find the height, the sine at alpha plus beta. We're talking about the point up here.
Okay.
The height from here to here, this height is the sine of alpha plus beta. This whole angle is alpha plus beta. Sine gives us a height, if this is a unit circle. So we know this distance right here is 1. You with me? Okay, so now I'm going to construct two right triangles. Not sure what color to use to make it clear. First, I'm going to construct the right triangle we get if we draw this down. So it intersects this at exactly 90 degrees. That's meant to be a right angle right there.
Okay.
So here's one triangle. Maybe we can make that a solid line red. So here's one right triangle. You with me?
Yeah.
And my other right triangle is I'm going to draw down from this point straight down. Here's my other right triangle.
Okay.
I'm going to draw one more right triangle.
Oh boy. Come on.
Let's do blue for this line, since it corresponds to the bottom blue line. We have a line parallel through here. A line parallel through here. This is supposed to be parallel to that.
Okay.
And so I'm going to do my last triangle here. Maybe we'll use red again. Which is the right triangle coming down from here.
There we are. That's what I'm looking for.
And this is also the right triangle.
Add the lines.
Now we're just going to calculate some lengths. The height to this point, this whole height, is going to be equal to this height plus this height. If I can figure out this height, and I can figure out this height, that gives me the total height.
That's true.
So that's what I'm going to try and figure out. Alright? Let's start labeling things that we know. This is 1, right? Look at this right triangle right here. This one.
Okay.
I know that this side is 1 and it's a right triangle. What is the length of this?
Whoa. It's not 1. Slightly smaller.
It's less than 1. What is it?
0.9.
No.
0.95.
Let me redraw this triangle over here, and I think it'll pop out at you.
Oh,
Redrawing that right triangle.
It's a tangent. It's cosine.
Oh, yes.
This is 1, this is beta.
Cosine.
What's this length? Cosine of beta.
Cosine of 1. Where's the tangent?
Cosine of beta. And what's this side?
Sine of beta.
Sine of beta. So, sorry. Sine. Alright, so let's relabel those. So, the height of this triangle is sine of beta. So that's right here. This black line is sine of beta. And this red line, maybe we'll use red again here to remind us it's associated with this line, is cosine of beta.
Simba.
You with me so far?
Yes.
Yes.
Now let's look at this distance and this distance.
Okay.
Now in general, let's go back. Remember what happens if I switch this to an r, then what is this?
R times cosine.
R cosine of the angle, and this becomes r sine of the angle. Now let's switch the angle here that we're talking about to alpha. So this becomes r cosine of alpha and r sine of alpha. Right? Now what if my r is this length, cosine of beta, whatever that is? If this is cosine of beta, that's how long this is.
Cosine of beta times
Then this
cosine of
length right here is cosine of beta times cosine of alpha.
That's true.
And this length right here is cosine of beta times sine of alpha. Right? So now we know these numbers. So this number down here is r times cosine of alpha. And this value right here is r
Sine of alpha.
times sine of alpha. Exactly. Okay. So we know what this height is. Notice that that was one of the two heights we were looking for. Because we said the total height is going to be this height plus this height. So I know this height, now I just need to find this height.
Yeah.
So now I'm going to look at this triangle. And we're going to redraw that over here. So I know that it's r, its hypotenuse is sine of beta, right?
Yeah.
And I know that it's a right triangle by construction. All right, what else do I know?
That the height is. We need angles.
The height is sine of 90.
We know our angles. We know our angles. What is this angle right here?
90 degrees.
No. 90 degrees is this. What is this angle?
Oh. Is it for?
What do I...
How do we know for sure it's 45?
It's beta subtract.
How is it 45? It's not 45.
It's not 45. It's not cut in half. Sorry, that's not the one we want to think about. We want to think about this one. What's this angle here?
That one?
Yeah.
30. It's 30.
Now our picture is awful, unfortunately.
Why do you want that one?
No, I think that's the one we know. Because let me try and make this intuitive for you. Imagine my arms are like this. You with me?
We're imagining.
So this arm is going to be this red line. This arm is going to be this black line. You with me?
Yeah.
So when I go like that, if my arms were like this, if I tip my arms up alpha, notice that my top arm was also tipped alpha. So I start out like this. This arm is the red. This arm is the black. If I tip my arm up alpha, I also tip this arm over alpha if they have to stay at 90 degrees to each other. You see that?
Yeah.
So my picture, I didn't, huh?
Okay, I figured out that angle.
It means, where are you going?
So it's beta.
So,
it's 90 degrees.
Where I'm going is not
subtract
this right
beta.
here is alpha.
Oh.
Because how much we tipped it, how much we drift from here should be alpha. But my picture's awful.
Wait, but that can't be because that.
So that's why I was doing this, because my picture's bad. When I tip up my arms, if I keep it at right angle, is there something here that's a right angle? Let's take two of these so you can see it better. If I put these at right angles to each other,
Okay.
and then I tip this one up, and I tip this one up so now it's making an angle alpha. I also tip this one in, so now it's making an angle alpha.
Oh, right, there you go.
So right here is an angle alpha, but now this is just, this tips forward the same much this tips away. So this tips forward some angle alpha. So my picture's bad. This should look much smaller than I actually drew it. So this and this are the same angle. Because they're however much I tip this line.
So you're saying that other angle's alpha too?
So this angle's alpha. No, this one down here is 90 degrees minus alpha, whatever.
No, the other one. Right next to alpha.
This one's alpha, and that one's alpha. And this one's alpha. They're all alpha. They're all, if I take this and I set it up at right angles, they're all how much I tip this. They all correspond to me tipping this.
Is there any definition of that or where to use that? Yeah, it's one of the.
Well, it's going to be corresponding angles. You draw this line as parallel to this line.
Well, for the first alpha and the one that's out there in the middle of nowhere. Just grab your
Now, this would intersect this parallel line. That would be alpha. That would be alpha minus 90 degrees. Now, let me see it. My picture's bad and it's throwing off intuition. But that's the way it works. I don't want to get stuck too much on proving the geometry of this. This is going to be some of your corresponding angle theorems from geometry. All right, so anyways, so now we know that that's alpha. Okay, so now let's figure out the height. What is the height of this? It's the height of this, where this is alpha. So this right here is alpha. So now we're going to kind of look at it sideways. What's this distance right here?
Sine of alpha.
Cosine of alpha.
Cosine of alpha times
R cosine of alpha. Right? So this right here is R times cosine of alpha. And so that's their height right here. This height right here is sine of beta. Why do I keep doing that? Sim instead of sine.
Interesting.
This right here is sine of beta times cosine of alpha. And this distance right here is
Sine of alpha times sine of beta.
sine of beta times sine of alpha.
That way back too. But you found your height you wanted.
But we found the height we wanted. Well, we're also going to have to do cosine next, so I wanted to fill in everything we need.
Oh.
Because we're doing them both in one go.
Well, that was just a mess.
So now we found out that sine of alpha plus beta is equal to this height,
Yes.
which is cosine of beta times sine of alpha. We typically write the sine first. Sine of alpha times cosine of beta, plus this height. And this height is sine of beta cosine of alpha. And that's our first identity here.
Down. Up. There you go.
Sine of, forget the negative at the bottom for a second. Sine of alpha plus beta is equal to sine of alpha cosine of beta plus sine of beta cosine of alpha.
That's what we got. Look at that.
That's what we got.
Well,
Now let's look at the cosine really quick.
Minus is going to be a pain.
No, minuses you get for free.
Yeah.
But we'll think about it in a second. Let's skip to cosine first. Let's look at cosine of alpha plus beta. What's that equal to?
Exactly.
What's the x coordinate here?
Playing the exact same way.
What's the x coordinate here? It's going to be this whole distance minus this distance. The distance, the x coordinate here, this distance,
That's why they call it.
is equal to the whole distance minus this distance. Or sorry, this distance minus this distance.
That makes sense.
Which leaves me with this distance, which is the x coordinate there.
Oh.
So, let's plug that in. What is this distance?
Cosine beta times cosine alpha.
I'm going to do the cosine alpha first, but same thing. Cosine of alpha times cosine of beta. Minus now this distance, which is sine of alpha times sine of beta. And if we look over here, cosine of, ignore the bottom symbol for a second, cosine of alpha plus beta is equal to cosine of alpha cosine of beta minus sine of alpha times sine of beta. All right,
See?
now let's make sense of what would have happened if we would have instead done alpha minus beta here. So alpha would have brought us up, and then beta would have brought us back down.
Yeah.
So we would have done this height minus this height.
Yeah.
So that would just put a minus sign here.
Well, that'd get a negative answer. Because alpha 1 is smaller.
It can come out negative. You can have a negative height. That's fine.
Negative. Flip.
It just can't come out more than negative 1.
Okay.
So there's nothing wrong with it coming out negative number. And then cosine of alpha minus beta. So cosine of alpha gets us here. And then when we do cosine of beta, some rotation this way, then that's going to add a little bit of length to it.
Whoa, what? Yeah. A little bit of length in the opposite direction. That would add a lot of length.
No, not necessarily.
Not as much as the alpha. That would subtract length. Yeah.
So alpha, and then if we did alpha minus beta,
That'd make it
then that would have brought this piece, our beta would be coming down right here, we'd be drawing it out like this, right? Crossing our unit circle.
That'd make it tiny.
And so we would have gotten however far over this shifted us.
You go backwards, so it'll go to the. It'll go to pi.
And then we'd be adding that little distance to it.
Why that distance?
Because it would be the same triangles.
No, duh, that distance. Yeah. Whoa, why that? Stop asking why and just accept it.
You can play with it and redraw out the picture for minus.
Oh, there's it is.
Okay,
There's it is.
I just don't want to draw out a whole nother picture for the negative case. Because the positive case and negative case really aren't that different. Okay, so that did those identities. So we did that, we did that. Okay, now sine of 2 theta. The sine of 2 theta is equal to the sine of, we can write 2 theta as theta plus theta. And now we already know how to do the sine of the sum of two angles. The sine of alpha plus beta is sine of alpha cosine of beta plus sine of beta cosine of alpha. So this is going to be sine of alpha cosine of beta plus sine of beta cosine of alpha. Our alpha and beta happen to be the same in this case. So I get the same term twice, so it's just going to be two of those terms.
Lo and behold.
So there's sine of 2 theta. Now cosine of 2 theta is equal to, we can do the same thing. Now it's going to be equal to cosine of theta plus theta. Plug it in here, and we're going to get cosine of theta times cosine of theta minus, because we're doing the top case, minus sine of theta times sine of theta. Which is equal to, what's cosine of theta times cosine of theta? What's any number times itself?
Squared.
That number squared. So this is cosine squared of theta minus sine squared of theta.
That's so simple.
And that's the first one we get. Now we get that's also equal to this thing and this thing.
So cosine squared of theta equals sine squared of theta.
Now,
What? Oh, no, it doesn't. Yep.
now cosine of 2 theta equals cosine squared of theta minus sine squared of theta. Now, that's one way that we write cosine of 2 theta. We also write this way and this way. So let's get each of these. This one got rid of a cosine, this one got rid of this one got rid of the sine squared, this one got rid of the cosine squared.
Yes.
So let's just do that really quick. Going back to our most basic identity, I know that sine squared of theta plus cosine squared of theta is equal to 1. So sine squared of theta, if we're going to substitute that out, sine squared of theta is equal to 1 minus cosine squared of theta.
This is true.
Right? So I'm going to make that substitution. That's going to give me one identity. Then also if you solve this for cosine squared of theta, then you're going to get 1 minus sine squared of theta. That's the other substitution I'm going to use to get the other identity. But first, I'm not sure which one we're going to get. Let's substitute out the sine squared first. So rewriting this, we get cosine of 2 theta. Cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. But now, cosine squared of theta, I don't know, we'll do that one first, because why not? Cosine squared of theta is the same thing as 1 minus sine squared of theta.
Okay.
So make that substitution. So I get 1 minus sine squared of theta minus sine squared of theta,
1 minus 2 sine squared.
which is equal to 1 minus 2 sine squared of theta, which is one of the identities. Okay, that was the bottom one. Now this time, let's instead substitute out the sine squared. So we get cosine squared of theta minus sine squared is 1 minus cosine squared. So we're going to get a minus 1 and a plus cosine squared when you distribute your negative, right? And so this is going to be equal to cosine squared of theta minus 1. Okay, got the next identity.
2 cosine.
Alright, so we did all the ways that you can write 2 cosine.
What about otherwise you can write sine?
Sine of 2 theta we only write this way.
Why?
That's the only identity you have
Is
on
this
your
not
sheet.
Squared?
It's the only useful way to rewrite it. This turns out thinking about cosine of 2 theta this way, and this way, they're sometimes useful. I'm just deriving all the identities you have on your trig sheet.
On mine?
If you Google a trig sheet of identities.
So,
Oh, do you have one?
Yeah, right here. 3.
You have 3? Okay, so chances are this shows up on there somewhere.
Yeah, it does. I'm seeing it.
Alright.
Where?
Does it have sine of 2 theta shows up a bunch of different ways?
Yeah, no.
Okay, just has
I
that
was
way?
asking why it does.
Alright, so we did what your trig sheet has.
Yeah, this is almost identical.
Yeah, it's the common things. I just Googled the trig sheet and wrote it all down. Alright, let's do the next one. Tangent of alpha plus beta. This one's just going to use these two.
Ugly.
So you could already guess how to do this. We'll just do the plus case, the minus case is identical. So tangent of alpha plus beta, by definition, is sine of alpha plus beta over cosine of alpha plus beta.
These two.
Right. What is sine of alpha plus beta? That's sine of alpha times cosine of beta plus sine of beta
Sine of alpha.
times cosine of alpha
Over.
all over. I think I'm going to have to divide these terms, so I'm going to leave some space here. All over
Cosine of alpha times cosine beta.
cosine alpha times cosine beta minus sine alpha times sine beta. Now, we're trying to get tangent. Trying to get a tangent to come out of this. So I want this to turn into tangent. So I'm going to divide it by cosine of alpha times cosine of beta. I'm going to divide this by cosine of alpha times cosine of beta, this and this. I'm going to divide everything by cosine of alpha times cosine of beta.
Okay.
You with me? So I'm going to divide this by cosine alpha times cosine beta. I'm going to divide this by cosine of alpha times cosine of beta. I'm going to divide this by cosine of alpha times cosine of beta. And I'm going to divide this by cosine of alpha times cosine of beta. Okay, and what do we get? Cosines of betas go out, so we get sine of alpha over cosine of alpha, which is tangent of alpha.
Times 1 is 1.
Plus, over here, cosines of alpha go out.
Yep.
And so we're left with sine of beta over cosine of beta, which is tangent of beta.
Crazy.
All over, this is just 1, right?
Ooh, look at that. That was awesome.
Minus, sine of alpha over cosine of alpha is tangent of alpha. Sine of beta over cosine of beta is tangent of beta.
Is that what it gives us?
And that's what it gives us.
Yeah, look at the thing. 10 feet.
Tangent of alpha plus beta gives us this. Now, if we would have had a minus sign in there, then the sine of alpha, when we expanded it, this would have been minus, and this down here would have been plus. And you'd end up with a minus here, and a plus there.
Yeah.
And so there's a negative. Okay, so we did all that. Tangent of 2 theta, just plug in theta for both of them. So let's go back to the plus case. When that was plus, this was plus, and this was minus. So this was plus, and this was minus. So now let's look at what's tangent of 2 theta. Or in other words, what's tangent of theta plus theta? Well, that's equal to tangent of the first angle plus tangent of the second angle divided by 1 minus tangent of the first angle times tangent of the second angle. Now, tangent of theta plus tangent of theta is 2 tangents of theta
Over 1 minus tangent squared.
over 1 minus tangent squared of theta. Okay, there's a tangent of 2 theta. Good?
Yeah.
All right, let's do the half angle identities.
Oh, joy.
Oh, joy.
Peaches, peaches.
Half angle identities. The thing I remember about these is I had to start with cosine of 2 theta. So I know I start by messing with these to get these. That's what I remember. Outside of that, not positive. But we'll just think about it.
What? Use negative, not positive.
Let me see for a second here. Oh, using these two. Okay, I think I have an idea. So cosine of 2 theta is equal to 2 cosine squared of theta minus 1, right?
Theoretically, yeah.
I just rewrote out this using this identity.
Yeah.
So just using this identity, something we already proved. Now I'm going to rewrite, I'm going to say we'll call phi, should we do phi? Maybe we'll just do alpha. I'm going to say alpha let's see, what do I want? I want alpha is equal to 2 theta. That's the substitution I'm going to make. And then rewrite this out.
Okay.
So then what does that mean? In terms of alpha, then cosine of alpha is equal to 2 times the cosine squared of alpha halves minus 1.
Yep.
Doesn't change anything, we just relabeled the angle. Alright, now I'm just going to solve for this cosine of alpha halves.
Okay.
So plus 1 to both sides, and divide both sides by 2.
Okay.
So cosine squared of alpha halves is equal to cosine of alpha. First thing we did is add 1 to both sides, so plus 1. Then we divided both sides by 2. Now square root both sides. So cosine of alpha halves is equal to plus or minus the square root of cosine of alpha plus 1 over 2, which will be our cosine one.
I got it backwards. Shoot.
Addition is commutative, so that doesn't matter. Alright, now let's do it again. Reset it up, same exact problem, but we're going to start with cosine of 2 theta is equal to, this time we're going to use this one, 1 minus 2 times sine of theta, right?
Sine squared.
Thank you, sine squared of theta. Now, I'm going to relabel let alpha equal 2 theta.
Okay.
So then cosine of alpha is equal to 1 minus 2 times sine squared of alpha over 2. Now I'm just going to solve for sine of alpha over 2, and we'll be done. So sine squared of alpha over 2 is equal to cosine of alpha this one, I might lose you in the algebra if I do too much in one go. Let me move this to this side and that to that side. So we have 2 times sine squared of alpha halves is equal to 1 minus cosine of alpha. Move this over here, so plus 2 sine squared of alpha halves to both sides, and subtract cosine of alpha from both sides. You follow the algebra? Good with the algebra? Alright, now divide both sides by 2. So sine squared of alpha halves is equal to 1 minus cosine of alpha all over 2. Now square root it, and plus minus.
So what makes you able to identify alpha as 2 theta?
I'm just relabeling the angle.
Then you wouldn't get to relabel it back? Or else you have a whole different mess up.
No, it's just an arbitrary angle.
And 2 theta is still arbitrary.
Theta was completely arbitrary. Now I have it in terms of alphas, it's just a variable. It's like you're saying, I tell you we have some equation where f of x is equal to x squared. And you say, well, I want to do this in terms of y, where y is equal to 2x. Well, then f of whatever y you have, if y is always 2 more than x, is going to be 2x squared.
So you just do it for simplification?
It's just rewriting it in terms of a different variable. You can think about it as changing units. So instead of counting it in terms of degrees, I want to count it in terms of half degrees.
Okay.
Does it change anything if I talk about it in terms of half degrees? No. So that's another way that you can think about this, is it's like relabeling units. Coming up with different units, relabeling. Doesn't change anything. So if I know that sine of any angle over 2 is equal to plus or minus the square root of 1 minus any angle over 2, I can call that angle theta, I can call alpha, I can call it whatever. And this works for any angle alpha.
Okay.
Because any angle alpha can be expressed as 2 of any other angle. Okay?
Now tangent.
Now tangent of theta over 2. Alright. So tangent of theta over 2 is equal to sine of theta over 2 over cosine of theta over 2, which is equal to, what's sine of theta over 2?
It's the 1 minus
1 minus
cosine
of theta over 2, all over square root of 1 plus cosine of theta
over 2.
all over 2, which is equal to, the 2's go out, and we can write it all as one radical. Maybe we'll still keep it as separate radicals,
Square
but
both sides.
no,
Why?
you'll see. So we get 1 minus cosine of theta over the square root of 1 plus cosine of theta. You with me?
Yes.
Now we're going to
You
rationalize the denominator. I'm going to multiply this by 1. I'm going to multiply it by the 1 that rationalizes the denominator.
That's how it's like over theta.
Huh?
In my paper, they just combine it. It's because your paper's retarded. They put all of that in one radical. Yeah, it's retarded.
Oh, you could leave it like that, but I'm going to get the identity that my trig sheet showed.
What the heck? Nobody likes roots. Mine shows that too, but it shows 3. Mine shows 3. 3? Yeah.
Yours might have a typo on it. Anyways,
No. That's what I've been using all year.
let's multiply top and bottom by square root of 1 minus cosine squared of theta. Square root of 1 minus cosine squared of theta. This is equal to that times that. Oops, not squared. Just cosine theta, sorry.
That
Square root of x times square root of x is just x. Square root of something times square root of something is that something. Right? Now down here, what do we have? We're going to have a 1 times a 1. We're going to have a negative cosine times 1. We're going to have a positive cosine times 1. And we're going to have a negative cosine times a positive cosine. When it's all said and done, we're going to be left with the square root of 1 minus cosine squared of theta. You see that? Now, 1 minus cosine squared theta is the exact same thing as
Sine squared of theta.
take the square root.
Sine theta.
So this is equal to 1 minus cosine of theta all over sine of theta. Dun, 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 dun.
Work.
It worked.
That's square box. That's my third equation.
Alright, so I got that equation. Next, so we did all those, did all those, did all those. Okay, cool ones now. Law of sines. And then law of cosines. And then the way that you relate products and sums. And then that pretty much gives you the foundations for most of what you do in trig, right?
Yeah, but you're missing 50 or so equations. But only retarded ones.
Well, I'm not going to be able to do a year's worth of trig in one review.
Actually, that is all of them. Except this one paper which I've never looked at before.
It's going to be all the common ones for sure. We might miss some less common stuff.
I'm not gonna.
And I didn't do anything with complex numbers.
He has the product to sum and sum to product.
We'll go one way, and then we won't bother with the other. We'll product to sum, but sum to product is.
Ditto.
So, oh, we were on law of sine though. Let's do law of sine. So law of sine, this is a cool one. We pick any arbitrary triangle you want.
Okay.
Not necessarily a right triangle.
Equilateral.
Let's get a funky triangle. We don't want anyone with nice properties. So we're going to pick a triangle that looks like this. Hopefully that is not a right angle. That's not meant to look like a right angle.
Now it does.
It's bigger than a right angle. Or smaller, who cares?
To make it more.
Sorry. I tried drawing 3 very different sides and it came out like a camera.
Right 91 degrees and fine.
And this is alpha. I'm going to put A on the opposite side of alpha.
We're gonna go crazy. 91 degrees.
This is beta. And this is gamma. And as a convention, we call the side opposite beta B and the side opposite of gamma C. Do you understand all my variables? Okay. Now I want to drop from this point down to a right angle. So now I split this into 2 right triangles. You see that?
Yeah, I do.
And this line right here we'll say has height h. What is h?
Height.
Well, look at this triangle. What's the height?
This is the sine of alpha.
It's the hypotenuse times sine of the angle.
C sine alpha.
C sine alpha. So h is equal to c times sine of alpha.
Sounds like an appendix.
But now look at it from this way.
Okay.
How high is h looking at this triangle? It's the hypotenuse times the sine of the angle.
Yeah. Yeah, cosine B times.
So
No,
h
A sine
is
B.
also equal to the hypotenuse, a times the cosine of the angle. Cosine of gamma.
Cosine.
Or sine, thank you.
Sine. There. Oh, okay. Now I get it. Yeah.
Okay. So h is equal to that, h is equal to that, so those are equal to each other. Now, let's see, which way do I have it written here? We have the signs on top. Divide both sides by A, and then divide both sides by C.
There's no C on that one side.
I know.
If
So I'm going to divide this by A times C, and I'm going to divide this by A times C.
There's no A on the place.
So what are we left with over here? The C's cancel out, and we're left with sine of alpha over A
Law of sine
is equal to
C.
sine of gamma over C. And we could have done a similar thing if we would have made H, drawn a right triangle from this point, to show that this is also equal to sine of beta over B. Those are all equal ratios. So the sine of this angle over that side is the same as the sine of this angle over that side is the same as the sine of angle of the sine of this angle over that side. That's the law of sines.
This is the case.
All those ratios are equal. Now let's do the law of cosines, or the generalized Pythagorean theorem, as it's sometimes called.
Really, really weird one.
Not that.
Law of cosines. There's just so much weird to it. So much weird.
So now we're going to try and draw another triangle. That we're going to try and make it look very clear that it's not a right triangle. Alright. That can't be misconstrued as a rectangle, right?
There's no way
Well,
as to what it
So we definitely can't use a Pythagorean theorem for this, right? So we'll have to use generalized Pythagorean theorem or law of cosines. Anyways, let's label some of these. I want it to come out the same way as this. So I think I need to call this one gamma, so the formula comes out the same. So this is side length C,
Yeah. Well,
and then which one I call alpha shouldn't matter.
that's not that.
So if I call this one alpha, this is side length A, and if I call this one beta,
Well,
this one's
alpha-
side length B.
Alpha needs to be the bigger one. Alpha's alpha.
Doesn't matter. Okay. So we're going to do a similar thing here now. You're going to drop that down, call it H. What is H equal to?
Cosine of gamma?
Sine of gamma.
A sine of gamma.
A sine gamma.
It's equal to A times the sine of gamma. That's what H is equal to.
Also equal to C times the sine of alpha.
That's how you get law of cosine, sines.
Yeah,
Law of
let's-
cosines.
I wonder if I need to switch some. Let's leave it here for a second. Okay. And then this distance here, from here to here, I'm going to call that distance x.
Okay.
And what is x equal to?
From B to
X is equal to the C cosine of alpha.
C cosine.
It's equal to c
C cosine of alpha, yeah.
times the cosine of alpha. That's this distance, right?
Yes, sir.
Okay, now I know that c squared, using Pythagorean theorem, is equal to this side squared plus this side squared. So c squared is equal to h squared plus x squared, which is equal to, what is h squared?
A sine R squared. A sine
A squared times sine of gamma squared. Oops, gamma. That's this. Plus,
X squared. Which is C squared with sine of X squared. Sine of alpha squared. Cosine of alpha.
Okay,
See how it's covering right there.
oh, I don't want to use c in this one. Sorry. So we need to come up with another way to do this that doesn't use a c. Because I want c to equal something. Because we're trying to solve for c.
Okay.
So I don't want to use c in solving for c. So the other way I can describe x is it's this whole distance minus this distance. And that way I won't be using c. The point of this whole thing, we're using Pythagorean theorem. We're trying to figure out what c is in terms of other things. So I don't want to use c in coming up with this stuff. So this whole length right here is what?
H over
B.
X.
B. It's just b.
H over X right here.
Well, that's what CS is. H.
Yeah, but we're trying to
B. So this whole length is b.
X is minus.
And now we need to minus this distance,
Which is Y.
which is, we
B
need to solve for
minus
it.
X.
Oh, cosine of A
B
cosine
minus
of gamma.
X.
A cosine of gamma. So minus A times cosine of gamma.
Can't be B minus X divided by.
You with me? Okay, so now that's what we're going to plug in for x up here. Except for now we need square it, because it's x squared. So we need this thing squared. So we get
B squared.
b times b is b squared. We're going to have b times negative a cosine of gamma, and negative a cosine of gamma times b. So we're going to have minus 2
AB cosine gamma.
ab cosine of gamma. And then you have this term times this term, which is going to be plus a squared times cosine squared of gamma.
That's way too long. Nope.
Now, it's about to get real pretty.
So yeah, please make it pretty.
Alright.
The process.
We have a squared times sine of theta, or times sine squared, a squared sine squared, and a squared cosine squared. I'm going to combine these two terms, factoring out a squared.
So make it 1.
So I get c squared
That makes sense to me.
is equal to a squared times
Sine.
sine squared of gamma plus cosine squared of gamma.
Which is 1.
And then we have plus b squared, and then we have minus 2ab cosine of gamma.
There we are. I see something.
You see something? Sine squared plus cosine squared is
1.
1. So this is all equal to a squared plus b squared minus 2ab cosine of gamma.
Now it looks real pretty.
Now let's say you can find any c. That's a general Pythagorean theorem. It works for any triangle, not just a right triangle.
And you could just flip it.
If you know your a and your b and the angle, you can always figure out c. The Pythagorean theorem is a special case where your angle is 90 degrees. What's cosine of 90 degrees?
1.
What's your x-coordinate at 90 degrees? 0. So this whole term is 0. So you're left with c squared is equal to a squared plus b squared, when the angle opposite c is a right angle.
Yeah.
So it gives you the Pythagorean theorem in the special case where your angle is 90 degrees.
Yeah, so that's the other side.
Alright, so there's a lot of cosines. Alright, now let's relate products and sums together. And then we'll be done. Alright. So, let's write this out. What is cosine of alpha minus beta plus cosine of alpha plus beta? What's cosine of alpha minus beta? Looking at our identity.
It's that cosine of alpha times cosine of beta plus sine of
Cosine of alpha times cosine of beta
plus sine of alpha times sine of beta.
plus sine of alpha times sine of beta. Erase this. We're going to have to go over here. Okay. Now, let's do this. Plus, what's cosine of alpha plus cosine of beta? Once again, is cosine of alpha times cosine of beta, this time minus sine of alpha times sine of beta. What do you notice?
That's extremely long. And there's terms we cancel out.
These two terms cancel out. And these two terms are the exact same.
They add together.
So this gives me, this is equal to cosine, 2 times cosine of alpha times cosine of beta.
And so you just want to see that.
Now, divide both sides by 2, so we get cosine of alpha times beta, cosine of alpha times cosine of beta is equal to 1/2 of this whole side. Cosine of alpha minus beta plus cosine of alpha plus beta. And bracket. And there's that first one. Right?
Very high.
Alright, now let's do the second one. The second one is what happens when you have sine of alpha times cosine of beta. So, for this one, we're going to look at what we get when we have sine of alpha minus beta plus sine of alpha plus beta. What are these equal to? What's sine of alpha minus beta?
That is sine of alpha times cosine of beta minus sine of beta times cosine of alpha.
And then we have to do plus. What's sine of alpha plus beta?
Sine of alpha times cosine of beta plus sine of beta times cosine of alpha.
And what do you notice?
There are terms you can cancel out.
Yep, negative sine of beta cosine of alpha, positive sine of beta cosine of alpha, those cancel out. And this term is the same as this term. And so you're left with, this is equal to 2 times sine of alpha times cosine of beta.
But you could 1/2.
Now divide both sides by 2, and you get 1/2 of this is equal to sine of alpha times cosine of beta. Now doing cosine of alpha times sine of beta, that's the same thing.
Except one with negative.
What?
Negative sign is different.
And how it comes out here, you're going to do the exact same process out.
I bet so.
So that one, I don't even think it's worth taking. So let's skip straight to sine of alpha times sine of beta.
I concur. You already have the answers in front. Keep going.
So now we have, start with cosine of alpha minus beta minus cosine of alpha plus beta is equal to, what's that equal to? Cosine alpha times cosine beta
Minus
plus
plus
sine alpha times sine beta minus, now cosine of alpha plus beta. Remember, we're going to flip the sign because we're doing negative to each of the terms. So we have minus cosine of alpha cosine of beta,
plus.
and then we have minus minus, which is plus
Yeah.
sine of alpha times sine of beta. And what do we get? The cosines cancel out. We're left with 2 sines. Divide both sides by 2. You get 1/2 that is equal to the sines. And there we go.
Simple. Product sum.
So review of a trig sheet. 2 classes covered most of the stuff you cover in trig.
Yeah.
So that's why I keep telling you over and over again, trig's pretty easy. Everything's pretty connected. You really only need to memorize a few definitions. And then the rest of it, you can kind of just play with it and figure it out.
There's so much more to trig that they brought up though. Like,
Yeah, a lot of what they bring up are special circumstances. You probably did some problems where it's like an object traveling in a circular path. We didn't do anything here with graphing these things out and seeing the analytic geometry of the sine wave, the cosine wave. So there is definitely a lot more you can do. But when it comes to solving a trig problem, these are pretty much the identities that you need to be able to work with. And there's no reason that you have to memorize what each of them are. You kind of just think about it, come up with them.
right.
Anyways, so that will end our trig review. That will give you enough trig foundation that if you were to go on and do a calculus class afterwards, you wouldn't be in the dark.